All right, so let's discuss XML. All right, so we've been talking about storing information in permanent storage devices and infrastructures such as relational databases using MySQL, and we also discussed a non-relational database such as Mongo, where we are permanently storing this in a file system. And then these infrastructures such as MongoDB or MySQL, they provide an abstraction layer so that we can think about the data that is being stored in the as tables or as collections. This is obviously just an abstraction layer. In the file system, this might be stored in some other proprietary storage, in some kind of binary and in a compressed format. But the infrastructure, these relational databases and non-relational databases, they provide an abstraction layer, right, that allows us to think about the data in terms of tables and collections and foreign keys, primary keys, data types, and whatnot, right? And this is pretty much the same for any data storage strategy that you might consider. And we also discussed making available this data, regardless of how you're storing it, whether it's relational or non-relational. You're making it available to the rest of the world through RESTful APIs, right? And we saw that there's several conventions on how is it that you would map these URLs and whatnot to a data model that is encoding one-to-many, many-to-many, different types of associations and whatnot. Also, we discussed how the data that is stored in a file system using relational databases or non-relational databases, how that can be read back into memory through the use of JDBC or JPA, or in last time we met is we were using Mongoose. So at some point, the data is being extracted and retrieved from the database, and we're trying to make it available to the rest of the world, either through a user interface or through a console or through a workbench and tools like that. Now, oftentimes these the data that we're exporting and making available to the rest of the world usually represents a data model that might be convenient to us, right? We who own the data. We own the data, and we have our understanding what we mean by an order or a product or an employee or department. We have our own schema and we have our own relationships and how we decided to break it up into our particular normalized representation of that data. Now, oftentimes when we are integrating with the rest of the world, it's most of the times the whoever is integrating with us, right? It's their responsibility to parse the data in a particular way, and since they don't own the data, right, they are stuck what we can give them. It might be that our data model is fairly hierarchical and it's fairly normalized, right, and have lots and lots of little tiny queries that you needed to retrieve employees over there and departments over here and products in a different endpoint. Or it could be very flat where you load all the data and it's already contained, it's embedded. All the data is in one single query, retrieves huge amounts of data. It depends. Yeah. Now, oftentimes the whoever is accessing this data, usually they will have to do some kind of transformation, right, and convert it into their own data model, right? It might be that how we are exporting our data, how we understand what a product is, or an employee, or a project, the way we store it using our own schema, it might not be convenient, right, for other folks who are retrieving this data, and they might need to do their own transformations, right, and convert it into their own schema. So oftentimes we need to provide mechanisms by which we can repeatedly and predictably and consistently be able to convert data models, right, that are provided by third-party APIs we need to convert them into our own data models, right? And so we're going to explore some of those mechanisms and some of those concerns on how is it that we can, store data, share it with the rest of the world, and transform this data into different representations of perhaps equivalent representations, right? This is very common in industry, right, where we are trying to create interfaces between different enterprises that represent their data differently, right? Maybe you have a Ford Motor Company, large corporations that is trying to integrate with a tons of other suppliers, right? And each one might represent their piece of the data set, slightly differently, right? The way Ford Motor Company keeps track of all its data, right? Of the windshield and the seats and the steering wheels and the and the motor and the doors and whatnot, right? It obviously has a fairly extensive representation of the cars that it's building, the processes and whatnot. Now, usually this needs to integrate with supply chains, right? That are providing all the raw materials. They're providing all the bolts, are providing all the tires and the windshields and whatnot. They're providing all these things, and you want to be able to automate the process as much as possible. But these systems need to be integrated. If you need to automate it, they need to talk to one another. These systems need to be able to detect when you're running low on tires, and you need to do an automatic order of another million tires, right? So how do you say that you represent tires and the different sizes and the different vendors and whatnot? And if Ford represents tires using one data model, and Michelin or Goodyear represent their tires in a completely different data model. So oftentimes we need to do a lot of conversion between these two worlds, and so that we are all talking the same information, right? So that we can do integration. So we'll discuss a little bit, somewhat of those concerns. Usually, it's one of the more difficult problems of having disparate representations of the same data. Basically, a tire is a tire is a tire, right? But if you have different representations of these things in different places, it's really, really hard. Okay, yeah. So right now we've been looking at specific representations in a relational database, in a non-relational database, and of a particular data model. But oftentimes folks are not going to have access to any of these systems, right? We're going to have to make them available. Obviously not through the console. Folks are not going to be able to just log in and start using our database and start updating the quantity of tires, right? Instead, we'll be exposing some endpoints where folks can integrate, right, and plug in. And we need to be able to document the schema, and they will decide how they want to be able to transform and convert and integrate. So first of all, we'll obviously the representation of the data is fairly arbitrary. It could be very well that we decide that it's a comma separated value file, CSV file, right? And we're using tabs and new lines and whatnot to represent the data. Obviously, this is a very inefficient way of representing it, especially because data might be hierarchical. Right now, this is pretty much what we've been doing in a relational database, right? Everything's stored in tables, and the tables are two-dimensional, right? And they don't allow easy representation of hierarchical data. The only way that you can represent it hierarchically in a relational database is to have self-references, right? Where you might have foreign key, primary key, foreign key relationships, right? That allow you to create these branches and nodes of children referencing parents, and parents referencing their grandparents, and so on and so forth, right? Where you can create these very hierarchical structures. Now let's take a look at a particular format that became very, very popular towards the end of last century, and it was very, very relevant. Well, it still is. It's still very relevant today, which is the XML format, right? So the XML format, XML stands for Extensible Markup Language. It became extremely, extremely popular at the turn of the century when right before the .com bust, right? That folks were looking on how to integrate disparate systems, and they were exploring web services. Web services was a novel idea back then, and there was a lot of competition amongst the big corporations. The Oracles and Microsoft and of the worlds, right? They were battling it out on how is it that we would be able to provide an integration solution, and XML played a really really big part in that in that market. And it seemed that everybody had agreed that XML was the appropriate way of representing data. Folks were looking at how to integrate systems, and the lingua franca of the data that was being shuttled back and forth between the different enterprise applications was XML. So XML played a big role. It played the role that today you see more JSON. JSON is kind of taking over the world as an alternative data representation. It's a little sad, right? That JSON is kind of taking over the world, since XML, I believe it's a much better suited for very complex data representation. It has a much richer data set, right? And it can be strongly typed. References and things like that. Although JSON on its own is as well making strides in fixing some of its problem, right? For instance, we have now a JSON schema that allows you to describe documents, JSON documents, which is somewhat playing the role of the XML schema that also was very very important. Anyway, so XML is just a format, right, that allows us to describe hierarchical data, right? And we've seen it already. We've been using it in several XML documents, such as the pom.xml, and and certainly you've seen it also used in HTML. HTML is just one flavor of an extensible markup language document. XML schemas, also a very powerful idea, right? That you can describe the structure of XML documents, very very similar in idea of what a Java class is. A Java class, describes the structure of a piece of information, a data point, right? That you're going to have integers and strings and dates and whatnot, right? And then you instantiate particular instances of that class, which we call objects. So schemas play the same role as Java classes, right? It doesn't represent any one particular XML document, but it represents all the XML documents that might have that particular structure. And just like we use Java classes to instantiate, to validate, to make sure that these objects are all following the same structure, same thing. XML schemas are used for that, for creating new documents and validating that those documents fit this particular structure. So we're going to be using an example throughout today's lecture of using, again, the same theme that we've been using throughout the semester of talking about students and enrollments and courses and whatnot. So here's an example of an XML document. And one of the things that I'm going to point out, throughout our lecture, is that many of the same challenges, many of the same concerns that we have when we studied relational databases and tables and whatnot, and we were looking for functional dependencies, and we were trying to avoid redundancy, and we were trying to make sure that we implemented normalization. Many of the same concerns and that we had with relational databases, those were also concerns when we looked at JSON representations, and those same concerns are also going to be present here in XML. Regardless of what your underlying choice of data representation and storage solution, and you're always going to have the same kinds of issues, right? You're going to have to avoid redundancy. You're going to have to mitigate that you might have inconsistency in your data. That when you're going to do updates, you may make sure that you don't do more than one update. Normalization. All these same concerns that we introduced early on in relational databases are going to follow you regardless of what choice of data representation and data storage solution. So let's take a look at here at XML and see how those same concerns might follow you here into XML. Here we have an example of multiple enrollments. We see that there's an enrollment root element at the top. We see that an opening tag and a closing tag saying that this is a parent element that contains several course taken, right? And the course taken here have several attributes describing that the person who took the course is Ian, right? And Ian took this. Ian has a graduation year of 2009. The course that Ian took was calculus, and Ian took this course in 2006, and Ian got an A. We see that there's 3 of these Ians, right? So it looks like we are listing all the courses that were taken by Ian. As well, we have a couple here that were taken by Ben, right? And so just by looking at this data, right, we're looking for things that might be wrong with this representation, and it always depends on your understanding of the domain, some domain knowledge that you might bring to bear when you are looking at this data structure. So, for instance, one of the things that we realize is that the graduation year seems to be always the same. Graduation year 2009, 9, 9, 9, 9. So this might have been this could be innocuous, right? Might not be a problem, but my guess, right, or our guess, could be that that this is the enrollments for the graduation 2009. If our understanding is correct, that the intention was that this is a listing of all the courses that were taken in 2009. I'm sorry, that for the class of 2009, those that are graduating in 2009, right? If that's our understanding and that's what the intention was, then certainly this implies that there's redundancy in this data model, right? That we are tracking the same information over and over, right? Graduation year 2009, 9, 9, 9, 9. Right? We could very well be that that for some error or when we were calculating this, we could inadvertently, right, modify this value, and instead of 2009, one of them could be a 2010. In that case, the database would be considered inconsistent, right? Because the intention was that we would want 2009, and somehow 2010 slipped in there. So the same issues that of redundancy and inconsistency that we might find in relational databases, kind of follow us here. So we're looking at alternative ways that we could normalize this data, right, to avoid inconsistency, right, to reduce or eliminate the redundancies that might give us a risk of inconsistency. So, for instance, instead of repeating ourselves over and over that the graduation year is 2009, an alternative representation might be that we could grab this graduation year of 2009, instead of representing it here multiple times, we could maybe bring it up, at the top of the parent element and capture graduation year 2009 just once. Okay, so the same techniques that or equivalent techniques that we have in relational databases where we do normalization. Here, the implementation of normalization would be to perhaps represent that information that is common to all the records underneath, to represent it in a parent element. Okay, that makes sense. So same thing, but again, the only reason we might have caught the fact that this might be redundant, it doesn't mean it's not redundant because the values are the same. Right? Notice that that's different. That's different, right? It doesn't mean that the redundancy is because the values are the same. It's because the understanding of the query and the meaning of the data right, suggests that we should not have to repeat ourselves multiple times, because logically these values should always be the same. So if that's the case, then we should represent it only once. Notice that instead, right, if we would have come here and for year taken, and this would have all said the same thing, 2006, 6, 6, 6, 6, 6, right, 2006 all the way through, even though the values are the same, right, we always have to ask, well, what was the query, or what is this listing representing, right? If it's representing the graduation year for 2009, then even though the year takens are all the same, then the data is not redundant, right? They just happen, all these folks happen to take the course together, and obviously the values are going to be the same. Well, that's totally fine. If instead the question is that this represents all the courses that were taken in 2006, then yes, this would be redundant. Okay, and so year taken should, instead of being repeating ourselves, we would move it up to the parent element. That makes sense, right? The data representation only is considered to be inconsistent or redundant only by us understanding the meaning of the query of what the data is representing, right? Not because we see data being, always the same. The same thing here. The grades might all be the same. Grade A. Again, if this is not a listing of everybody who got an A, right? If this were a listing of everybody who got an A, then yes, it's redundant. We would not capture the grade multiple times. If instead this is not necessarily a listing of who got A's, then it's not redundant, right? These folks just happen to be very smart and they all got A's, right? So it's not necessarily redundant. So the understanding of redundancy and inconsistency, right? It depends what context are you talking about. All right, so let's talk a little more about XML. These are enrollments and course takens, right? These are all referred to as elements. The enrollments and the course taken, these are all elements. We say that the way, so elements is it's a generic term to refer to these data sets, right? The data sets of elements or course taken, right? That are capturing data points, right, of all the enrollments of all the course takens. Now, the way we write it, or the way we encode it in ASCII files, right? We use these what we call tags. So here's an opening tag and we have a closing tag, right? And now this opening tag and closing tag, notice that it has other tags underneath, right? It has other elements inside of it. We say that the enrollments element has a body, right? So course taken, all these course takens, right, are inside the body of the enrollments element. But notice that each one of the course taken, notice that it has this slash at the end, right? It doesn't seem to have a closing and an opening and closing tag. Instead, it's just one single tag, right? So we refer to this as a self-closing tag, right? And it does not have a body, right? It just self-closes itself, right? So just some jargon. We also call these values that allow us to configure some values, some properties about the elements. We call them attributes. And attributes are just name-value pairs. So name of the attribute and then the value of that attribute. And it has that syntax of name equal value, right? And usually the values are uses the double quotes to represent the data. All tags must be closed. The tags can be mixed case, so it doesn't really matter if you're capitalized or lowercase, right? You can have tags within tags, right? To define arbitrarily complex pieces of data. So here's our discussion earlier, right? That we were pointing out the fact that we were capturing graduation year multiple times, right? And was introducing redundancy. So a better representation was to capture it only once in the parent. Notice that here that the syntax that we are following for capturing this information is that we're capturing some information about the courses taken. We're using attributes to capture that information. right? So for instance, for the course taken, we would capture maybe the name, the title, right? And that's totally fine, right? We would capture, if the piece of information that you're capturing is something trivial, such as a string, right? Like the name, the title, the year taken, then attributes are fairly appropriate, right? It's very short, it's a small piece of information. But we could have, instead of used attributes, we could have used nested elements, in the body of the course taken. So for instance, here we have an example that might be capturing the same information, right? We have the graduating students, right, as a root element, and then that it contains several students, right? So here's one student. The name of the student is Ian. The graduation year is 2009. Notice that we could have alternatively chosen student and then the S name, right? The S name Ian inside of as an attribute of student, right? Instead, we chose to use an element, right, that capture the information for the name. Same thing for graduation year. We could have captured it as part of the student element. It could have been an attribute called graduation year 2009. But again, we chose to capture the same exact information, but using a nested element. And whether it's one or the other, whether you choose to use attributes or to use nested elements, it's entirely up to you. If it's something so trivial like this, like a small piece of string, then folks prefer to use attribute name value pairs. If it's something that it's a list of things, collection, or the data is extremely big or extensive, then the preferred way is to capture it using a nested element. So for instance, for Ian, we are capturing courses, and these are all the courses for Ian. Notice that this is a more normalized implementation, right, where instead of capturing 3 different records of Ian, right, notice that here we have Ian, Ian, and Ian, right, and these are the 3 courses that Ian took in 2006. Notice that this alternate representation, right, it's capturing Ian and the graduation year just once, right? And then instead of capturing Ian 3 times and graduation year 2009 3 times, right, this one is a little more normalized, right? This one is a little flatter. This is a much flatter, denormalized representation from this one. This is a much more normalized implementation where we're capturing the information of the name of the graduation year just once, right? And then here we have all the nested list of all the courses that Ian has taken in from 2006 or whatever, 2007, and the list of the courses, including the title, the year that was taken, the grade. So this is certainly a much more normalized implementation. Again, the same kinds of things that concerns that we have in relational databases, non-relational databases, XML databases, right? It follows us along, right? Functional dependencies, normalization, redundancy, all those concerns follow us along. So here it is. So there's the list of the first student, and presumably you're going to have multiple students, capturing information about their particular courses that they took. Also, another way of viewing or considering XML documents is that they implement a hierarchical data set, right, where you have the top level XML element, what we also refer to as the root element, that then might contain a list of other siblings, right, elements that are embedded inside of the parent element. So here we have multiple lists of students, which is exactly what we have here, right? We have the graduation students, and then student Ian, and then student, all the different students. I forget what the name were, Ian and Ben, right? So you have Ian here, and then you have another student that follows with Ben. So yeah, so graphically you would have a parent graduating students, and then Ian, Ben, Alice, Bob, and blah, 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 right? And then inside the student, you might have information about that particular student, including the name of the student, the year that they graduated, and then the list of courses that they took at a particular year and whatnot, and the grade that they got. Okay, so certainly you can think of this, right, as nodes, right, inside of a diagram, right, of a graph, right, and where the actual data is represented at the leaves of this inverted tree, right, whereas all the elements allow us to create all the branches of this hierarchical tree.